Welcome, scholars. We actually have quite a lot to accomplish in this lesson, so let's get to it. We're actually covering Chapter 2, Big Concept Number 1, Power and Radical Functions. Objective, I am learning to graph and analyze power functions. I am learning to graph and analyze radical functions and solve radical equations. So first things first, a power function is any function of the form f of x equals ax to the nth power. A power function is also any type of monomial function such as f of x equals a or f of x equals a times x to the nth power. And a and n are both non-zero constant real numbers. Now here's the thing, this is something you really want to ingrain in the back of your head. It's really going to help you with the remainder of Chapter 2 and going forward. So when we take a look, it says let f be the power function of f of x equals ax to the n. So I'll just rewrite that real quick so we can see f of x equals ax to the nth power. If n is even and positive, it's going to make the U shape. And the n behavior, which is the big thing that will help us the most, is the limit as x approaches negative infinity of f of x is positive infinity, and the limit of f of x as x approaches positive infinity is positive infinity. So if your n is even and your a is positive, you're going to have that happy smiley U shape. However, if n is negative, even and a is negative, you're going to have that frowny, and that'll change that n behavior as well. Now, not to negate the domain, the range, the intercepts, the continuity, symmetry, the minimum, the decreasing, or the increasing, those are the easy stuff. I know you all have that, but I really want you to pay attention to that end behavior, because if you're able to figure out this end behavior, the rest of this will fall into place. All right, so now if n is odd, and a is positive, and just a reminder, we're talking about f of x equals ax to the nth power. If that n is odd and a is positive, it has that cubic function shape. Because, once again, n is odd and 3 is odd. Right? And so that actually changes that n behavior. And then if n is odd and negative, we reflect it about that y-axis, and our n behavior is reflected in that as well. So if anything, take a moment, pause the video, write this down, this big chunk of information. It is also in your OneNote class notebook on Teams, and I've also linked it on your weekly schedule. So this is a biggie. Keep it. Write it down. All right, so reminder, monomial functions with an even degree can also be solved algebraically in the sense that f of negative x equals f of x, then it is even. And likewise, an odd degree says if I replace negative x in my function, it'll turn the entire function negative. So we're actually going to take a look at an example real quick. We are going to graph and analyze the function. We're going to describe the domain and range, the intercepts, the end behavior, the continuity, and where the functions are increasing and decreasing. So first things first, we have an a that is positive and an n that is even. So that tells me right off the bat, I'm going to have that U shape. So I know I'm going to have that 0, 0. All right. So even before I graph that, because it is that U shape, I know what my domain is going to be. I know that my domain is going to be negative infinity to infinity. I don't even have to graph this yet, just because of what we learned. My range starts at 0 and goes to infinity. And this is all because I know that a is positive and n is even. My intercepts, I only have the one at 0, 0. My end behavior, the limit of f of x as x approaches positive infinity equals positive infinity, and the limit of f of x as x approaches negative infinity is positive infinity. And we get that all from the fact that a is positive and n is even. We also get that it is continuous from negative infinity to infinity. There's no discontinuity, there's no breaks, there's no jumps. It is increasing. It is that U shape from 0 to infinity and decreasing from negative infinity to 0. Once again, we know all of this simply because A is positive and N is even. All right. So what does this graph look like? Well, we know it's a U shape, so we're just going to have that U shape. Now, with this exponent, the higher that exponent becomes, the flatter that U shape is at the base. So if I were to put in the number 1, I would get 1 to the 4th, which is 1/2. So it's going to right around here. And same with negative 1. But if I were to put 2, 2 to the 4th is 16. And then 1/2 of 16 is 8. So I go from 2 to 8. And because it's that U shape, it's negative 2 to 8. So let's go ahead and draw that curve real quick. All right, so there's Mrs. Younger's attempt at drawing that beautiful curve. However, I do have Desmos pulled up over here. And if we take a look, this is what it'll look like as well. A nice U-shaped, a little wider, flattened at the bottom because that exponent is of 4. All right, going on to the next one. Now we have A is negative, and N is odd. So based on the information that we gathered, we know that my domain is going to be negative infinity to 0. My range, why did I say 0? Negative infinity to infinity, because it's that cubic shape. My range is the same, negative infinity to the infinity. My intercepts, I'm just going to have the 1 at 0, 0. My end behavior, cubic shape, reflected across the y-axis. So I know it's going to come up here and go somewhere swooping down. So end behavior, the limit of f of x as x approaches positive infinity is negative infinity. And the limit of f of x as x approaches negative infinity is going to be that positive infinity. It is continuous on the entire graph, negative infinity to infinity. It is increasing nowhere. And then it is decreasing everywhere from negative infinity to infinity. All this information was gathered simply because we recognize that A is negative and N is odd. So we know that we have the 0, 0, the negative 1, positive 1, and the positive 1, negative 1. And then we're going to make that cubic shape. So there's Mrs. Younger's freehand version of negative x to the 7th. But if I pull over my Desmos, I see here's my negative x to the 7th. Because that exponent is bigger, notice we are closer to that x-axis, especially if I scroll in a little bit more. All right, going on. So now we're going to actually talk a little bit more about the reciprocal functions. So one thing to remember is f of x equals 1 over x or x to the negative first mean the same thing. And they are both undefined at x equals 0. And that is because we cannot have that 0 in that denominator. Similarly, other functions such as f of x equals x to the negative 2 or f of x equals x to the negative 3 are also undefined at x equals 0, and that is because you cannot have a denominator of 0. As a result, when n, that exponent, is less than 0, the graphs will have functions that have discontinuities, aka we're going to have what we call asymptotes. So let's take a look at this graph right here. We know that A is positive, N is less than 0. So we're going to have that discontinuity. Now, taking a look at our domain, we know that nowhere on our graph can we equal 0, which means we have to account for the fact that we're going to not equal 0. So we have that union, negative infinity to 0, union 0 to infinity. It can have any number but 0. And so we have to represent that in both the domain and the range. The intercepts, because it cannot touch 0 on the x or y axis, there will be no intercepts. My end behavior. So we know the limit of f of x as x approaches positive infinity is going to equal 0. And that is because as we get closer, as we put in number after number into that x, it actually makes our fraction smaller. So the same is going to apply to as x approaches negative infinity. We're also going to get to the limit of 0. For continuity, we are actually discontinuous, or there's discontinuity at x equals 0. And we are increasing from negative infinity to 0 and decreasing from 0 to infinity. So what does this look like? Well, let's throw in a couple points. We know we're not going to be able to touch that y-axis. We know we're not going to be able to touch that x-axis. So if I put in the point, let's say 1, 3 times 1 to the negative 2, I'm going to get 3 halves. So 1 to 3 halves is right around here, 1 1/2. But if I put in the value of 3, I have 3 over 3 squared, which is 1/3. And so what happens is I get super, super close to my y-axis, and I get super, super close to my x-axis, but I'm never going to touch. So let's go ahead and draw that rope. All right, so here's Mrs. Younger's beautiful drawing. She really does not do freehanding very well when it comes to graphing. So here's a take a look at it on Desmos. Now, that is an even exponent. What happens when I have an odd? Well, let's take a look. Notice I'm reflecting across the origin instead of that y-axis. So it does look different. We still have that discontinuity though at 0, 0. All right, next example. Let's talk about x to the 1 over n, or the nth root of x. Same thing, x to the p over n is the nth root of x to the p. If x is an even integer, then the domain must be restricted to non-negative values. So that's the big thing. If x is an even integer, then the domain must be restricted to non-negative values. All right, y'all, even as I said that, I knew it was wrong. So if n is an even integer, then the domain must be restricted to non-negative values. I kept on saying, that doesn't sound right, that doesn't sound right. All right, so yes, if n is an even integer, then the domain must be restricted to non-negative values. So let's graph and analyze each of these functions, and then we're going to describe each piece. So first we have our f of x equals x to the 5 halves. So how could I rewrite this? This is the same thing as saying f of x equals the square root of x to the 5th, where 2 is that index, meaning my square root. Because n, my index, is even, that means I am restricted to non-negative values. So my domain can start at 0 and go to infinity, which means my range will also be at 0 and go to infinity. My intercepts will have one at 0, 0, and behavior says the limit of f of x as x approaches positive infinity is going to equal positive infinity. Now, do I have an end behavior for when x is approaching negative infinity? I do not. And that is because I'm restricted to non-negative values, which means I cannot go in that negative direction. For continuity, I'm continuous at, and I have to start at 0, and then I am go from there. And then I'm increasing from 0 to infinity. And am I decreasing at all? No, I am not, because this is a root function. So we have no decreasing. All right, so now I know that with this root, I have the 0 and I have the 1. But what happens? X to the 5 halves. What is that going to look like? Well, it actually makes this funky shape like this. And that is because I'm taking the root, but I have an exponent that is larger than 2. Right? And if we were to pull the Desmos over, that is what it looks like on Desmos. And what happens if I have a negative exponent that is also going to be a radical? If you take a look, it becomes reflected across that y-axis. We have some asymptotes once again. All right, so now let's actually talk about radical functions. So x to the p over n is the same as the nth root of xp. So if I take a look here, this is what we call the exponential form. And this is what we call the radical form. They both mean the same exact thing. A radical function is a function that can be written as f of x equals the nth root of x to the p, where p and n are positive integers greater than 1 and have no common factors. So once again, let's take a look. If I have an n that is a positive integer, it is going to have that square root shape. But if n is odd, it's going to have the cube root shape. Imagine that, cube being odd. And take a look at our n behaviors for an even n. The limit of f of x as x approaches infinity is infinity, but for an odd n, we have an n behavior in both directions. The limit of f of x as x approaches negative infinity is negative infinity, and the limit of f of x as x approaches positive infinity is positive infinity. Once again, this is something you need to write down. Take a moment, pause the video, circle it, put big exclamation points. This is something you need to remember. All right, so we're going to go and we're going to do another example. So here we have an n of 4 and a p of 3. So that means my index is 4, which means it's going to have that square root shape. And then my p is 3. So domain, 0 to infinity, just like we looked at. Range, same thing. Intercepts at 0, 0, and behavior. The limit of f of x as x approaches positive infinity is going to be that positive infinity because we have nothing in that negative direction. It is continuous at 0 to infinity. It is increasing from 0 to infinity, and it is not decreasing one bit. And so when we take a look at this function, We know it's that square root shape. So it's going to have, here's my 0. It's going to have a shape something like this. And when we pull over our Desmos, there it is. Notice, I'm just freehanding it. Unless it says graph specifically, you won't need a table of values. So if it says graph specifically, do a table of values. Otherwise, just do a quick sketch. Use your graphing calculator, use Desmos. That way you just have an overall idea of how that graph is supposed to look. So now we're actually going to take a look at radical functions, specifically radical equations. And a radical equation is any equation in which the variable is in the radicand. So to solve a radical equation, you isolate the radical expression, then raise each side of the equation to a power equal to the index of the radical expression to eliminate the radical. However, when we raise both sides of the equation, it can lead to extraneous solutions. So here's the biggie. Always check your work. And so we're going to go through 2 examples of what I mean. All right, so we need to isolate the square root. So in order to do so, we're going to add 2 to both sides. So now we have 2x plus 2 equals the square root of 100 minus 12x. Now, our index is a 2 right here, so that means I'm going to square both sides. When I square a square root, the square root cancels the square. So now I have 2x plus 2 times 2x plus 2 equals 100 minus 12x. So when I go ahead and distribute, and remember first, this term goes by everything in here. The first term goes by each term in the second set of parentheses. So we get 4x squared plus, oopsie, 4x, and then the second term by everything in the second set of parentheses, plus 4x plus 4 equals 100 minus 12x. So simplify further, 4x squared plus 8x plus 4 equals 100 minus 12x. Now we have no more radical. Let's go ahead and move everything to the left-hand side so we can isolate that x value. So we subtracted 100 for both sides and added the 12x. So now I have 4x squared plus 20x minus 96 equals 0. This is where we need a factor. First thing I notice is that we have a GCF of 4, so I'm going to pull out that 4. I'm left with x squared plus 5x minus 24 equals 0. This is a trinomial with a leading coefficient of 1, so I need to find the factors of negative 24 that will add up to a positive 5. So that's x plus 8, x minus 3. All right, now I'm going to set each of these factors equal to 0. So x plus 8 equals 0, x minus 3 equals 0. So I have x equals negative 8 and x equals positive 3. So I have 2 solutions. Wrong. Do I know for a fact I have 2 solutions? I don't. So we need to check. So the first one I'm going to check is x equals negative 8. So I'm going to go back to the original. I have 2 times negative 8 equals the square root of 100 minus 12 times negative 8 minus 2. This becomes negative 16 over 100 plus 96 minus 2. Negative 16 equals the square root of 196 minus 2. Negative 16 equals 14 minus 2. Negative 16 equals 12. Wait a second. Does negative 16 equal 12? No. So x equals negative 8 is not a solution. All right, so now we're going to go over here and we're going to check x equals 3. So I have 2 times 3 equals the square root of 100 minus 12 times 3 minus 2. 6 equals the square root of 100 minus 36 minus 2. 6 equals the square root of 64 minus 2. 6 equals 8 minus 2. 6 equals 6. Does 6 equal 6? Yes. X equals 3 is a solution. So you always need to make sure you're checking your work, especially with these radical equations. All right, so that is the end of our notes for today. I did have another example planned, but I think we got the gist of it. I hope you have a great day. If you have any questions, please do not hesitate to message me. I am always here to help. Bye, guys.